By Divya Oberoi from NCRA. So, okay. Thanks. Good morning, everyone.
Good morning, sir.
Good morning, sir. 11:45. Sure. So, we have time till for about an hour, right? Yeah. So, they're requesting that please use microphone. Sure. Right. Easy. Okay, is this better? You guys can hear me? Okay, so we have time for about an hour. I don't have a specific set of slides to go through. I have a lot of slides. I don't intend to go through all of them. The idea is to have some sort of a reasonable conversation and to sort of excite a little bit of interest in what this whole business of doing astrophysics is about. Right? You're here to attend the winter school. You probably have some expectations as to why you are here, what you want out of it. Does anybody quickly want to say, what are you looking for? Why are you here in the first place? Of all the million things you could do, you have chosen to be here for this winter to attend, to sit through some boring lectures, or maybe not so boring lectures, rather than being outside.
Restart a career in astronomy.
Why a career in astronomy?
I want to know who I am, what my origins are, so I don't go to be absolutely
Not ancestry.
yeah, ancestry.
To understand all the fancy terms when we look at any astrophysics books or whatever texts we look at.
Anybody else? Something you want to add to what has already been said?
There's so many unanswered questions in astronomy that fascinates me. The work upon it.
Sure. So in many ways, astronomy is easy to relate to and we work for. That's rather than having you stare at that boring title, I thought I'll put an image of the sun. This is what I'm going to talk about, the sun and the heliosphere. My name is Divya. I work across the road at NCRA. I'm usually addressed by the name DIP. So you're welcome to call me that. Okay, so I also wanted to start by saying why is it that we want to talk about the sun in the first place? Why we want to study the sun? Before I give you my answer, I thought I would ask you, or why do you think we should bother about studying the sun?
What's the brightest object in the sky?
So, sorry, just one. Raise your hand, somebody, and I have you.
The sun is the brightest object in the sky, so and it's nearest to us. So obviously, one should be interested in that.
Okay, very good.
Sun is the only source of energy for us.
That is also largely true. Yeah.
It's the only thing big enough to get us interested because other things we need a telescope.
Moon is just about the same size as the sun.
But it doesn't emit light on its own, so that way it's independent.
So you like big shiny things.
Sun is useful for us in many ways.
Like
For light and
light.
Major hydrogen source.
for
Very
plant
far
growth.
away now. I mean, how does hydrogen there help you? Is somebody at the back? Yes.
It is the closest star to us. And if you want to study the stars, you have to study the sun and you have to know how the stars grow.
Sure. But you want to ask just behind you, you want to
It affects major like atmospheric conditions on the earth, like the life on the earth is like majorly due to sun. So even that.
Right. And so there's just one second. Yeah.
It's just we're curious, right? I mean, it's just another thing in the universe. It impacts us, and we're curious about it. We want to know about it.
Apparently, humans' physical maturity is decided by how many times we revolve around the sun, so it can't hurt to study it.
I'm not so sure about that. Maybe
We have a huge abundance of data compared to any other astronomical object.
Okay. So all of those are pretty good reasons. Most of them are very good reasons. I'll give you my list shortly in the next slide. So once we agree on why should we study the sun, then I'll briefly introduce you to the sun, something which goes by the name of the heliosphere, and say something about how the sun impacts the earth, only a small part. And then if there is time, I'll talk about the rest of the stuff. The last one I'm sure I won't get to, because that's on slide number 70 or something. So why? The sun, like some of you already said, is really the reason why we exist. Right? It's the primary source of all energy on the Earth except for nuclear and geothermal. Like nuclear energy is independent of the sun, geothermal energy is also independent of the sun. But most of us are still not relying very much on nuclear or geothermal. So, and for most of evolution of human life, right, of not just human life, life on this planet, sun is the reason why life evolved on this planet in the first place. Then the astronomical reason is, of course, that if you want to study and understand other stars, you might as well start with your nearest one. Right? So, because this is a star which allows you to study it in absolutely great detail. Right? All other stars, except for a tiny few, are just pinpricks in the sky. They are unresolved by any telescope, most of them. Right? While this guy is half a degree in size. You can see it in great detail, you can study a lot about it, in excruciating detail. There's so much detail that you don't know really what is important and what is not when you're looking at the data. Okay. Then talking a little bit about heliosphere. Heliosphere is really the region around the sun. Let's just call it that for now. That's a fantastic plasma lab. It provides us an opportunity to study matter under conditions of temperature, pressure, density, which we cannot create in our labs at all. Even the solar plasma, even the best MHD simulations which are done, they are about 10 orders of magnitude off in terms of what we are able to simulate, leave aside creating it in the lab. Okay. So that's the sort of differences. And then there are practical reasons as well. The practical reasons I list simply as space weather. We now have a lot of spacecrafts flying around. We ourselves travel quite often about 10 kilometers up out of the Earth's surface when we were flying. At those heights, already some of the things which happen on the sun begin to impact us. So there's this entire new field which didn't exist maybe a couple of decades ago called space weather, which is becoming quite important now. So that's a practical reason why you want to study the sun as well. In addition, there is a lot of talk, not just talk, you actually see global warming, you see the climate patterns around you changing, so on and so forth. And we know, yes, that there are things which we are doing on this planet which are impacting the climate, like the amount of carbon dioxide or other greenhouse gases which we are adding to the atmosphere. But all said and done, the energy which is incident on the Earth is from the sun. Right? So while you should study your greenhouse gases, you should also study the total energy which is incident on the Earth, because that is also going to play an important role in whatever global warming comes out to be. Right? So that plus more philosophical reasons, then, and also stuff like, a lot of astronomy is like mountaineering. Why do you climb a mountain? It's not what to anybody else. It's there, you get a thrill out of it. Right? And it's a feeling of having achieved something, done something. It has the additional advantage of some intellectual satisfaction. Right? Wow, there was this problem which nobody could have answered for however many years, and now we know. Right? And it's because of something which I did. Right? So all those reasons, those are, I'm sure, partly the reasons why you're here, because you're excited by problems which we don't yet understand, which we have not yet managed to solve. And sun has plenty of them. Okay, so to get started, I need to keep track of time. Here's some numbers about the sun. Size, right, about almost 10 to the power 9 meters, 7, 10 to the power 8 meters. So it's about 1/100th of the size of the Earth. Is one good way to remember that. Sorry, I said it the wrong way. It is 100 times the size of the Earth. If you look at the mass is also roughly 1,000,000 times the mass of the Earth, which already tells you that the average density of these two must be very similar. The Earth-Sun distance is about 150 million kilometers, 1.5 10 to the power 11 meters. It's also referred to as 1 ASIC, 1 astronomical unit. Measured in units of the radius of the Sun, it's about 215. And that's again a good number to keep in mind. How far away you from the sun. The effective temperature, and by this number I mean the effective temperature of the solar disk which you see. I'm not advising you to look at the sun. Please don't look at the sun. It's very bad for your eyes. Even in the total solar eclipse, unless you're really in the company of experts, don't choose to look at there are 30 seconds of totality or something, but as soon as the first bright thing comes out, you stare for it for longer than a few seconds, it's going to go on your retina. So please don't do that. The effective temperature of the visible disk is about 5,800 Kelvin. Right? The luminosity, how much power it is emitting, is 4 × 10⁻⁶ watts. And then there is this quantity called the solar constant, which is about 1.4 kilowatts. That is the amount of energy incident at the top of the Earth's atmosphere from the sun. That's a fantastic number, 1.4 kilowatts per meter squared. So if we were somehow able to figure out a way to harness this energy, that would totally take care of a lot of our energy issues. There are fantastic plans which are already being made about having sort of geostationary giant mirrors, which are going to give you megawatts worth of power directed at some place on the ground, where you convert this very intense beam into use that to heat something up and use that to drive your turbines and so on and so forth. How old is the sun? It's about 5 billion years. It's a middle-aged star. It's also a fairly normal star, G2 plus star. Okay. So a look inside the sun. So it's quite amazing that that we're sitting 150 million kilometers away from the sun, but we know in quite great detail what is inside the sun. It's also, I personally also find it amazing that our medicine is able to figure out in great detail what is inside our mind. It has no moving parts. It has just a bunch of tissue, a lot of fat, but they can tell you exactly where your vision is and where other things are and what goes wrong when you go slightly crazy and so on. Okay, that's a digression. So at the center of the sun, it's about 14 million Kelvin. These numbers are, you look at different diagrams, you will find numbers to differ a little bit. That depends on the levels of approximation which various people did while they were arriving at this figure. But if you were to talk to, let's say, the research groups who are into helioseismology and so on, they'll give you really precise numbers about what we are expecting here. That is the place where the thermonuclear reactions are taking place. That's where your hydrogen atoms are being combined to form helium along with some release of energy. That energy on top of this thermonuclear regime sits something called the radiative zone. It's called radiative zone because the most efficient means of transporting energy in this part of the sun is via radiation. Right? There are these three modes which we have now, right? Radiation, conduction, convection. Right? So in this part, it is the radiation which is most efficient at transporting this heat. That is why it is called the radiative zone. Even though it takes, different estimates vary, but many, many years for a photon which is released here to show up here, just because of the path it has to take, which has, it's a random walk with a lot of scatterings. On top of this radiative zone sits something called the convection zone. That is because now the matter has been cooling down enough, due to the temperature in the convection zone, not so much. So that it is now able to absorb these photons, and as it absorbs these photons, it becomes hot. As it becomes hot, it is possible now for convection to set in. And that is where it becomes the most efficient means for transporting heat now is convection. These convective zones, they have sort of many layers. It is trying to show them like this, that there is larger convective cells on top of which sit smaller convective cells, on top of which sit still smaller convective cells. These guys we are even able to see using our telescopes, and I will show you the picture a little bit later. And you see a little bit of stuff which is coming out, and I'll show you something more about that. So something which I completely left out in this figure was I was talking primarily about matter. Right? In addition to the matter which is here, and the energy flow and temperatures and so on, there is also magnetic field of the sun, which is really the piece which makes the sun most interesting. Okay. So here is an example of how all of you are familiar with at least the term sunspots, and some of you have seen them Probably all of you have seen pictures of sunspots. What they are eruptions of the magnetic field from the solar surface. Now what is happening here is that in this region, it is the convection which is the agent for transporting heat from the bottom, from the top of the radiative layer to the top of the photosphere. Now when there is a strong magnetic field, it actually inhibits convection in that region. Therefore the heat transport there slows down. That is the reason why these places appear as dark spots on the surface. Right? And they can be almost 1,000 Kelvin or a little bit more cooler than the neighboring regions. And this is the convection cell which is being shown here, and so between there has emerged this magnetic field. Now, how many of you have had a course in plasma physics? Okay. Never mind. So, when you have magnetic fields and highly ionized plasma, they begin to behave like beads on wires, right? So your plasma forms your beads, and your magnetic fields become your wires. Okay? So just like in a necklace or something, you cannot move the bead without moving the wire. The same thing begins to happen in the plasma. So whatever is the magnetic flux which is threading some region, that plasma is forever married to that magnetic field. It cannot be moved away from that. Okay? So now what happens depends on which has more energy. If it is your magnetic field, which is a very stiff wire, and your bead is a flimsy plastic thing, then that magnetic field will decide what the bead will do. Right? The bead is going to remain confined along these magnetic fields. On the other hand, if your bead is like a thick, heavy iron ball, and your wire is like a flimsy thread, the bead is going to drag the wire along wherever it goes. Right? So these two situations are defined as in terms of a ratio called plasma beta, where beta is the ratio of magnetic energy to the kinetic energy of the particles. So in the lower corona, in this region, the sort of place where we are talking about, this is a low beta environment, and so because the magnetic field is strong, the magnetic field must sit in the denominator in this particular case. Okay. As you rise much higher, the magnetic field energy begins to go down because it goes as sort of squared of the root, squared of the v squared in a given area. Because it is the same magnetic field which is going further and further up. V squared is dropping quite significantly, electron temperature is not dropping, and therefore it slowly begins, the kinetic energy of the electrons begins to dominate the magnetic energy which is there. So this underlying structure, if you were to look at it in a real photograph, this is a white light image taken from a satellite by the name Hinode, which means sunrise in Japanese. This is what it looks like. So you see a central dark patch, which is called the umbra. It is surrounded by a not as dark patch, which is called the penumbra. And then you see all this patchy region, which is here. Right? Now, if you were to look closely, you already see a lot of interesting things. Right? I mean, clearly, this is just a cartoon. Real life is really very interesting. There's an enormous amount of detail which you could see. Now, what you know from this sort of picture is that, okay, you know that magnetic monopoles don't exist, right? So magnetic field is always continuous. So if we were to not bother about what is happening below this, we are still sure that whatever has come up must come down, right? So in this picture, if we are sure that no field is going outside this image, everything which has come out, and I don't know which one is north and which one is south, but let's, for the sake of argument, call this north. Right? Whatever has come out of here must go back in here. But these two are not the same size. Right? In fact, this seems to be sort of already broken up into things. So clearly, whatever is coming out is not coming out like a smooth bundle, and it's not going in like a smooth bundle. Right? It can bifurcate, it can break up into various pieces, and the density inside those could be different. Not only that, if you look at these parts, you see sort of fibers, right? It does not look like a simple gray patch. It has a lot of structure. Now, something must be giving rise to that structure. And what is really giving rise to that structure is that this magnetic field is really like a bundle of spaghetti or noodles. So it has large overall shape, but that shape is coming from a very large number of smaller bundles of magnetic field which are twisting and turning and tangled around each other and so on. And it is those which you are seeing in this sort of a picture, in these regions. What you are seeing here are what are referred to as the supergranules. The granules which are large enough for those convection cells to potentially see. Any question? If anybody has any question, please feel free to ask me. I will reserve the choice of taking the question then or later.
So those granules are made up of that magnetic field trap?
So these granules you're talking about?
Yeah.
These granules are just the visual appearance of these convection cells.
Okay.
So it's basically that the matter where it is rising is brighter and where it is falling, it has cooled and therefore it has become heavier and now it is going to fall. Those are the darker boundaries where it is falling. Okay, right? So the magnetic field is really very interesting. Okay. And this, like I was telling you earlier, if this magnetic field energy is the dominant one, it is going to trap the plasma. That is what you are seeing here. Right? If I can, I just want to switch off one of these lights so that you can see the picture.
So maybe
I'm not sure if there's making much of a difference. Okay, I hope the contrast is somewhat better. So you can imagine a lot of these things to be like the cartoon which I was showing you earlier. It's a magnetic field which is erupting and then is going back. And of course you can't see magnetic field. Right? What you are seeing here is electrons. These are really high temperature electrons. This is image from a different satellite by the Solar Dynamics Observatory. This instrument is called Atmospheric Imaging Assembly. This particular image, I think, is at about 600,000 Kelvin. What I mean by that is that there is one particular emission line which you are seeing, which is preferentially emitted by atoms of hydrogen at 600 Kelvin, 600,000 Kelvin. Very good. Okay. Now this magnetic field, right, which I was talking about, I was telling you that these sunspots are the place where this magnetic field is emerging, is erupting from the surface, and you can see it extend well above the surface of the sun. Images like this.
Sir, you said that those curved lines, those are the paths of the electrons that we are seeing, is it?
I am not saying that. I am saying that those are the wires, and the electrons will be confined along those. But I did not say that they will trace the electric field like that. They will in fact gyrate along the electric field.
Because that should be transfers to the magnetic field.
Okay. In fact, if you were to look at a very carefully taken photograph of the sun at a solar eclipse, which is what this is, you would see evidence for magnetic field not only above the sunspots, everywhere on the sun. That is what I'm trying to show you. This is an H-alpha image of the sun which was put in later, just to make it more dramatic. But this image itself was taken during the solar eclipse. And a lot of heavy image processing has been done to highlight the structure which you are seeing because of the magnetic field. Right? Now you can see that, okay, this sort of looks like what you might expect from a bar magnet. Right? There is a north pole and a south pole, and these lines are going out. In addition to that, there are a lot of these other structures which are there at a range of scales. Right? There are these larger things, it's called a helmet streamer. Okay? These are these smaller things, similar in nature but smaller in scale size. There are also various other things which are sort of fainter, is not that easy to see. But there is evidence for magnetic field everywhere. Right? Not just close to your active regions, but everywhere. And all of this magnetic field which you have seen, a lot of it is so-called open magnetic field. By open you mean magnetic field which is actually not going back to the sun. Or you could say that, yeah, this is going out, maybe going out to infinity, This is also going up to infinity, and what is going out of there must equal what is coming in from here. So in that sense, the magnetic flux of the sun is conserved, is zero, but this field line is not going to explicitly come and join this one. Okay. Now a little bit more about the structure of what is happening on the surface of the sun, or just a little bit below the surface of the sun. So this plot shows you as a function of height the temperature on this axis and density on this axis. So, the chromosphere sits right on top of something called the photosphere. The photosphere is what we see with our eyes. And the temperature there is a little bit below about 10 to the power 4 Kelvin. So it's similar to what is there on the photosphere, but it has this peculiar structure where it begins to drop for a while, and then it goes through a sudden rise. That the region where it rises is what is called the transition region. For obvious reasons, it's transitioning from being at close to 10 to the power 4 to coming out to something like 10 to the power 6. And this is of order just a few hundred kilometers or maybe 100 kilometers or something like that. So in a very narrow region, right, suddenly the temperature is going to shoot up by 2 orders of magnitude. That's really dramatic. And correspondingly, this dashed line gives you the density, which is what is here. The density drops in the same region from, say, from close to something like 10 to the power 14 to something like 10 to the power 9. So that's again a 5 orders of drop in density. Again, over a very small region. Okay. And this is really, and this region is completely permeated by these magnetic fields. Okay. So in this particular, the analysis which went into getting these temperatures and densities didn't take the magnetic field into account in this particular paper, but even if you do that, they are not dramatically different. It's hard to take the magnetic fields into account properly because magnetic fields are inhomogeneous. Right? They not only they have a direction, they have different densities at different places. It's a vector, right? So you can't really make a simple plot like this if you wanted to take the magnetic field distribution into account. You will have to do some sort of averaging of various things. Okay, so this is the complete set of images which you get from an instrument by the name solar analysis observatory. It observes the sun all the time. That's its mission in life. It observes the sun in 13 different wavelengths simultaneously. And all of them are what are shown here. This is really, the first two are not electromagnetic wave images. This is a Doppler graph. So it is looking at the shift in the wavelength of some particular line which is coming towards you or moving away from you. Right? And that forms the basis of the data which you need for helioseismology. The next one is a magnetogram which shows you via Zeeman effect the strength of the magnetic field which you are measuring. And the blacks are one polarity, negative, the whites are the other, positive polarity. And that shows you a cluster where you see a lot of magnetic field of the sun. These guys with this guy, these are now all different electromagnetic wavelengths. This is it's a continuum white light, something similar to what we see with our eyes. And that shows something what you expect to see. Right? There are sunspots which are in the region where there is a lot of magnetic field on the surface of the sun. There is a big darkening as you go away from the sun. And as you go forward, there is this guy at 1700 angstrom, which is something is coming. So that's about 4,500 Kelvin, cooler than what we have on the photosphere. And it's showing you, I don't want to get into what it's showing. Okay, let's go to higher temperatures, where I can talk a little more sensibly. Okay, 10,000 Kelvin. Now you are seeing, if you remember this figure, so by about 10,000 Kelvin, you are now sitting here. Right? You are probing the edge of the chromosphere. So all these lines which are at about 10,000 Kelvin and below, they are called chromospheric lines because the region of the corona which they are probing lies in the chromosphere. And you're now beginning to see that, okay, this spot, which was really dark here, is beginning to appear bright here. So it still has a dark spot at the center. The contrast has reversed. What was dark here has become brighter here. And that continues to happen as you keep going further and further up. 50,000, 600,000, million, 2 million, 2.5, 6, 10, right? So even though these sunspots, which were dark, right, in the visible light, when you are looking at very energetic particles or very energetic plasma, they are bright. Because they have so much magnetic field that they are able to trap, they have to do two things. They have to somehow energize these particles, somehow they have to heat up these particles. Right? That is why they are there. Something must be heating up these particles to millions of Kelvin. They have to heat up and they have to confine. If you were to heat it up and let it go, then it won't be sitting there. Right? So not only are these magnetic fields, not only do they have the ability to heat up this plasma to very high temperatures, they also have the ability to keep it confined. So that means magnetic field intensity must be much, much greater than the kinetic energy corresponding to even a 10 million Kelvin electron plasma population. Notice another thing. Till about here, the limb of the sun is very sharply defined. Right? You can draw a line, you can say, okay, this side there is sun, that side no sun. Notice what begins to happen as you move forward from here. You can begin to see some fuzz here. Maybe if you look closely, there is some fuzz. Here it is very clear. Right? There's the limb of the sun is no longer that clearly defined. Now, why might that be? Well, that is because there is this hot plasma which is sitting on top of the solar disk. Right? Not only it is sitting on top, it is everywhere. It's not that it is close to the active regions or something like that. Wherever you see, it's there everywhere. In whatever wavelength you want to see. Even at 10 million Kelvin, you can see some evidence for that there. Right? Far away from any active region. That is really interesting. Just because I work at radio frequencies and I won't get to talk about them unless I was to steer the talk in a very different direction, I am going to introduce just a little bit of radio. So these are all electromagnetic spectrum. All of these guys are spectral lines. I also wanted to show you a very different part of the electromagnetic spectrum, which is now in radio waves. And I'll talk a little bit later about what exactly are the emission mechanisms and what are you seeing here. But this is what it looks like. These are, the lower two rows are from higher frequencies, 17 gigahertz and about 5.7 gigahertz. And these, you will say, look roughly similar to what the images at some of the higher frequencies were looking. Well, wherever there are active regions, you see something bright here, and the disk is very well defined. If you go to lower frequencies, and this is about 400 megahertz, give you a sense for wavelengths, 300 megahertz is 1 meter in terms of wavelength. So this is 400, so about 75 centimeters in wavelength. If you were to look at this guy, and this white circle which you see here is supposed to define the optical limb of the sun. Once again, you see there is a lot of emission which is coming from outside the sun. Right here. And it can have a lot of structure, it can have big holes. In fact, these are referred to as coronal holes, which these are different successive days, which is stable. You can see it rotate with the same expected rate of rotation of the sun. So they can be structures which are long-lived, and there is a lot of emission coming from heights well beyond the known limb of the sun. Right now, these are the only 2 points which I want to make, even for the radio waves at low frequencies. This should no longer be there. Okay. The coronal heating problem. So this is a sort of preamble to what is referred to as the coronal heating problem. And I showed you that there is this corona which is sort of hot, which we know is at about 1 million Kelvin, right? And the fact that this is at about 1 million Kelvin has been known for a long time. So 70, 75 years people have known that This is the very dense. Everybody is also agreed that the source of that energy, which is heating up this plasma, must be beneath the photosphere. We also know from our first law of thermodynamics that heat cannot flow from a colder body to a hotter body, no matter what the mechanism of that transport be. Right? No radiation, convection, or conduction. And we need a lot of heat. We need something like 10 to the power 7 Earths per centimeter square per second, or you're probably more familiar with SI, so 10 to the power 4 watts per meter square, right, to heat up the corona to this particular temperature. You can keep pumping that energy. This corona is not going to stay warm or hot on its own. It's going to radiate away its heat. That is why this is a sustained heat flux of 10,000 watts per meter square, which you have to provide. This number has also been known for 35 years. What is also known is that, remember I was earlier talking about there being convection on the surface of the sun, and there being magnetic field on the surface of the sun, and the medium through which this magnetic field is rising is a turbulent convective medium. Right? Now, as you are going to be churning this plasma, which is magnetized, you are actually going to have to do work on that medium. Right? So everybody is also agreed that this business of moving the magnetic field around from where it is rising is what is referred to as foot point motion. Foot point is your anchor point of the magnetic field on the surface of the sun. If because of turbulence that thing moves around, it's called foot point motion. So this convective turbulence can do enough work, has the required reservoir of energy to do the work, to store this energy in the magnetic field. That is also agreed upon, and it's been done since 90s. And in fact, some Indian scientists played a very key role in establishing this, in particular Arnab Rajchandri at the Ministry of Science. In fact, he has a wonderful book called The Third Cycle of Nature. It's too expensive to buy individually, but if you ask your libraries to buy it, do go and take a look. It's probably here in the IUCAA library as well. So what is the problem? The problem is that we have not been able to find evidence for this enormous amount of energy to making its transition from the photosphere to the corona. And in fact, it's called the coronal heating problem because the coronal temperature was recognized to be that high first. The chromosphere is also at about 10,000 Kelvin. The chromosphere is much denser. So it turns out, in fact, that the amount of energy which is needed to heat up the chromosphere is even larger than what is needed to heat up the corona. And assuming that the same mechanism which is responsible for one is also responsible for the other, you would say that the chromospheric heating is even a larger problem. Good. Okay. So I'm not going to say too much about the solutions or the answer to the coronal heating problem, except for saying that it's still unsolved. That is one thing to say. There are two different ways people have been approaching this. One is that, well, what do you have to do? Somehow you have to extract energy from magnetic fields. Right? So one way which people have been exploring is that, yeah, we know there is this foot point motion. If it is possible for me to set up some waves in these magnetic fields, right? And we know there is good description of what these waves are like, etc. These waves could propagate up, and then if you could get them to dissipate, then you have managed to transfer energy from a cooler medium to something else, and that might be able to heat things up. So the waves in magnetic field are referred to as alpha waves, and you would read about them as you begin to do your chemistry or plasma physics courses. And so for few decades now, many decades now, people have been building more and more sensitive instruments to look for evidence for presence, propagation, and dissipation of these waves. And now we are actually able to find the evidence for their existence and their propagation. The problem, however, is that these waves, there are two problems. One is that these waves don't seem to be giving up their energy. To the best of our instrumentation, we can see them propagating. So unless you extract, and they're propagating into regions where corona is already hot. So that means it has not yet given up its energy, but the corona was already hot for some reason or another. That's one problem. And the other problem is that if all of this heat flux was to be transported by these waves, the amount of energy which we see to be in the waves right now is not sufficient for that. So this, even if this were true, even if we were able to dissipate this energy somehow, there's not enough of it to heat the corona to its melting level. The other thing which you could do is to say that, okay, make use of phenomena which goes by the name reconnection. So what happens in reconnection is that you should think of magnetic fields like rubber bands. So as I twist and tangle them and make their geometry more and more complicated by twisting them around, I'm actually storing energy. As soon as I release it, it's going to try to come back to its lower energy state. What happens in magnetic fields is that if I'm twisting and turning them, as I know I can do because of my convective foot-point motion, I have now stored a lot of this magnetic tension in these magnetic fields, and they are going to look for opportunities to relax. They find these opportunities to relax via this reconnection process, and what happens there is that when oppositely oriented magnetic fields come close to each other, they can release the excess tension which is stored in them and just reconnect. And the energy which goes missing from the magnetic field is actually used to heat up the local plasma. And that is again one way of extracting energy from the magnetic field and dumping it locally in the plasma. So now if something like that had to happen, it has to happen everywhere on the sun, because like we saw, corona is hot everywhere. And there are also other diagnostics or other features which such a phenomena should have. Right? In that, because corona is hot even away from the active regions, it has to happen there as well. You also know that in order to put sufficient amount of energy into these events, into these individual coronal magnetic reconnection events, they have to follow a certain power law. Now, a lot of work has been done on that, and we find that we have not yet found the features or these nanoflares is what they are called, which meet the criteria for coronal heating. Okay? So as of now, this is an unsolved problem. A lot of people, including myself, are working on that, and including people at IUCAA. If you want to talk to Durgesh.
So what causes twisting of the like what are the causes?
So the primary cause for that is that the region through which this magnetic field is emerging is a turbulent region. So that plasma is sort of flowing in. Think of a velocity flow which has structure at a range of scales. So it is twisting, turning, and that is what is causing these magnetic fields to twist and turn. Okay, so now so I wanted to sort of talk about a different aspect of the sun, and that is to do with the things will change on the sun, the dynamics of the sun. Okay. Now, just another question for you. So my talk, I believe, was supposed to start at 11:45. We want to 12:45. What do you have after that? Lunch, which probably starts at 1 or something. So I'll maybe overshoot just a little. Okay. Fine. So this is, well, the sunspots we know actually are not long-lived things themselves, and I chose this picture just because of the curiosity of putting on that. What I wanted to talk about really is this. Okay. So on the x-axis here is time, which is measured in years, and it goes all the way from 1900 to 2020. Right. So sun, in fact, is like I think somebody mentioned earlier as well. The sun was the first astronomical source whose observations mankind started. These data actually, I'm not showing it here, but they go back to before the invention of the telescope. And since the invention of the telescope, man has kept, or mankind, or whatever civilization has kept, pretty meticulous records of the sunspots which were seen. So there was some crazy guy somewhere or the other who would every day, on every cloud-free day, make observations of the sun and note it down in a notebook. And from 1700s, that knowledge has been preserved to this date. It's quite an amazing thing to think about. There are two things which are shown here. The y-axis is something called the daily sunspot number, and that thing is the light blue thing. And you would see that it's very jagged. It can change very rapidly from maybe one day to the next, or within a week or something like that. And then there is this thick blue line which is there, which is the monthly average sunspot number. That is much smoother. Just because it is much easier to interpret a smoother time series than a jagged time series, most people work with the monthly averaged sunspot number. So what comes to your mind when you see something like this? Well, you see that it goes up and it comes down, and it goes up again and it comes down again. In such functions, you would say must be periodic. If you were to look at that in some greater detail, you will find that it's not periodic in the sense of your sine wave periodicity, because these periods change from one cycle to another. Like it has an average period of something like 11 years, but we have seen cycles with periods ranging between 9 years and 14 years. It's quite a variation. Also, you would notice that these amplitudes can be very different from one cycle to the next. Something which people find very curious lately is this is about the time when the space age began, 1958, I think, or 57. Is when we started to launch satellites to actually study things. Since that time, this is the number of sunspots which you've been getting at the maxima of every solar cycle has steadily been declining. It's not easy to see on this particular scale because it's sort of 120 years compressed here. But here, there were 100 days, 100 consecutive days when there was not a single sunspot on the sun, which had not happened since the start of modern science, let's say. Okay, fine. So not only is the solar cycle manifested in terms of the number of sunspots, it is also manifested in terms of where these sunspots are on the sun. That is what is being shown in this particular plot. So this is now going back a little further, 1870 to 2020. For obvious reasons, such a plot is called the butterfly diagram. It was made first by Carrington. And what is shown on the y-axis here is the latitude, the solar latitude of the location of a sunspot. And the colors tell you something about how many of them were there. So this is if the sunspots covered more than 1%, they were in a particular latitudinal strand. They were painted here. That particular point was painted here. It was greater than 0.1% red. There was something there, but not much. It was given between 0 and 0.1% is black. So now you see that if, just to guide your eye, I have drawn some vertical lines here. These lines are roughly at the minima of these cycles. When you look at them to see where they end up in the top panel, at the minimum, or just beyond the minimum, the sunspots begin to form at about plus minus 30, 35 latitude. As the cycle progresses, these guys tend to come closer and closer to the equator, and then suddenly they disappear and begin to reappear again at the higher latitudes. That's a cycle which they have been following, and people have done a lot of work on trying to find out if the sort of magnitude of the sunspots in the two hemispheres is similar, equal, unequal, and a lot of studies have been done of that sort as well. But clearly there is a long-term trend which we've been seeing for hundreds of years. And so this must be something fundamental. And this I won't be able to get into explaining where it comes from, but it is related to what is called the dynamo cycle of the sun. The sun has a magnetic field. And you learn that if I had just an isolated body with its magnetic field and I did nothing to it, there are good reasons why that magnetic field will decay. If I have to sustain a magnetic field, then I must do something to keep regenerating that magnetic field. And that thing is called a dynamo. We are all familiar that a current gives rise to a magnetic field. Right? So it's basically an application of that. It's called the solar dynamo. And if you were to, so Arnab's book is a great place to learn this from. If you were to read a little bit about it, it will tell you how you could explain a cycle like this based on what the current thinking is about the solar dynamo for the sun. And in fact, it also turns out that even though on a plot like this cycles looks like it is about 11 years old, in reality, if you were to also take into account the polarity of the magnetic field, it becomes a 22-year-old cycle. So what happens is that, let's say, if you were to look at the field at the pole of the sun, in one cycle, let's say that field is positive. In the next cycle, it becomes negative. And if you were to define your complete cycle as when the field at the North Pole was restored to its original state, it would then become a 22-year-old cycle. Okay. So this solar cycle, till now we've been talking about it in terms of presence of active regions and how many are they and where are they and so on. It is actually seen in a lot of other parameters as well. And some of them are what I've shown here. So the blue one is the familiar sunspot numbers, which we were just talking about. There is a dark curve which you would be able, the red curve, is the annual irradiance, and the yellow is the daily irradiance. Irradiance is again the total amount of power which is being radiated by the sun, integrated over the entire volumetric luminosity, I call it, all over the electromagnetic spectrum. That you can see has enormous variations. Right? There is also something called the 10.7 solar radio flux. This 10.7 is the flux emitted by the sun at 10.7 centimeters. That's just the wavelength that is emitted. That is shown in this particular color, and you see that it often tracks the other variations very well. Right? And then there is something called the solar flare index. Solar flare index is just a standard formalism which people use to find out how active the sun was, or how many flares of what strength took place as a function of time across some part of the solar cycle. So all of these things, they have differences in detail, but they rise at the same time, they fall at the same time. In these two guys, they even rise to about the same heights. Right? While in this guy, they seem to have a lot more spread. But that was the previous solar cycle, and this was a part of evidence for saying that something is changing on the sun, something much longer term is changing on the sun, which we want to understand.
Which vector decides this period of 11 years?
So that comes about from the natural properties of the system, how large the system is, and the strength of what is called the meridional circulation. It requires me to go into things which I was not originally planning to include, but basically there is something called differential rotation on the sun. That basically means that the sun does not rotate like a solid body. Different parts of the sun are rotating at different speeds, and in fact the equatorial belt is rotating faster than as you go to higher latitudes. Now if you were to imagine a magnetic field which is permeating all this plasma, and even if you start with, let's say, a line which is going smoothly across the latitude, if I make the equatorial part rotate faster, right, starting from here, it is going to become like this, and it is going to keep becoming like this, right? Because the equator is moving faster and so on. That is one part of the story. There is also something called this is the north-south part, which is called the poloidal, from one pole to the other. There is also something called the toroidal field. This is the toroidal field because this is being wrapped around the azimuth. Similarly, there is a circulation path. If I was to sort of draw a cross-section of the sun, there is some sort of a flow which is also taking place perpendicular to the equator. Okay, so this is the equatorial plane, this is the pole, and there is this flow as well. It's an interaction between this rate of flow and this rate of flow, which brings you to a particular time scale. And that for our sun happens to be 11 years. Okay. And the same solar cycle is visible in, for example, in an image like this, which is showing you this is from an sort of ancient X-ray imager, among the first ones which were sent, IUCAA. And it shows you an image of the sun for a representative day for each year. So there are 11 years here. The start of the solar cycle is here. The minima of the solar cycle, I should not have said start. This is the maxima and that is the minimum. Right? Naturally, this is what you expect. Right? The more active regions here, so you expect sort of more bright things at higher temperatures, while there's practically nothing there. So you would still notice that the fuzz around the sun is still there. Right? So that thing is not gone away. So your background corona is still hot, whether or not you are at the solar minima or maxima. This was an X-ray. This is in EU. So EIT stands for Extreme UV Imaging Telescope, which is on a little more modern satellite. This also shows you 11 pictures, one representative picture from each year. Minima is at the back, maxima is up front. And again, you can see evidence for there being many more active regions here as compared to there. The sun looks pretty much featureless. Not only in that, you also see the same features in something called the solar wind. Now, I have not mentioned anything about the solar wind till now, but I did show one of the pictures which I was showing of the solar eclipse. It had magnetic field going out all the way to the edge of that image. So this magnetic field is what is confining this plasma. If this magnetic field is open, then it provides a path for this plasma to escape, right? And that is what becomes the solar wind. And that is what is being shown in this plot. Once again, the maximas are up at front, the minimas are at the back. There is no color scale associated here, so I will tell you. So these deep blues, what is being shown here is the speed of the solar wind, the radial velocity or the radial speed of the solar wind as it is flowing out. These deep blues are something like 800 kilometers a second. And these reds are something like 250, 300, probably 300 kilometers a second. What it is showing you is that when you are at the minimum, you have high-speed solar wind coming out from everywhere just outside the equatorial belt. What that is really telling you is that there is a lot of open magnetic field there. Because that is what you need for these particles to flow out unimpeded. If you don't have enough magnetic field, then the solar wind has to do a lot of work to flow out, and that is what leads to a reduction in its speed. And that is, so you don't have much open magnetic field in the equatorial belt. That is where the speed is slow. But as you go towards a solar maxima sort of a condition, this very nice dipolar structure which you would expect from a dipole magnet, let's say, is very disturbed. And you no longer have large regions of open magnetic fields. Occasionally there can be some like this or this, and these are what are referred to as coronal holes. This is what is also seen in this picture. This is the same picture as I had showed you earlier. This was taken in 2006, which is close to a minimum. This is a similar picture, similar as in taken during an eclipse, but not as nicely image processed, but taken during a maximum. Looking at this picture, there is no way now where you can identify that, say something like this must be the north pole and this must be the south pole. So that beautiful dipolar structure of the magnetic field is completely wrong. Because this is the time at which you are in a phase in your solar cycle that this field is actually not dipolar. It is in transition from being aligned with one dipole to the other dipole. And that is the phase when you have solar wind like this. There is not much open magnetic field at all. Okay, so talking about solar wind, actually there are suggestions much earlier as well from these guys, but these two people, Paul Annert and Ludwig Biermann, were among the first people who used the fact that whenever you look at comets, the tails of the comets are always directed away from the sun. They use this simple fact to say that there must be something coming out of the sun which is pushing this thing away. This was the sort of argument which they were making. And they did a fair amount of work to quantify what this might be like. Now, if you were to take a modern picture of these guys, you will in fact see that there are two tails to these comets. There's something called a dust tail and there's something called a gas tail. If you want to find out why there are two tails and why they are not both along the same direction, in fact, you would see that this thing is slightly curved while that thing is straight. And that's something, if you want, you can look up Wikipedia and it will tell you why there are two tails. Okay, this was a very exciting time actually in solar physics and solar wind history, because very soon after this, Eugene Parker, who by the way is still around and doing good science, and was also the thesis supervisor of Arnold Branchology, who I was mentioning earlier, he put forth a theory for why there must be solar wind. Till then, people were basically talking about something called a hydrostatic solution. Hydro because it's a fluid, so it has to be defined in terms of fluid mechanics, so hydro. Static because they did not think it is something which is a flow. They thought that it is just like the Earth's atmosphere, which has a stratification, but it is still, it is static. So they had been coming up with a similar explanation for the solar wind, but that had not been meeting various, it was giving rise to impossible things, in the sense that the density of the solar wind must be very, very high, even when you are hitting the interstellar medium. So he came up, he was the first one to come up with a wind solution, which basically meant that this is something which is moving, it's a flow, and that is what was solar wind. It was fantastic because he published this paper in '58. Next year, there was a Soviet probe which was launched, Luna-1, which actually measured the plasma in the solar wind and came up with measurements which were very, very close to what Parker had predicted. That was fantastic. In whole of astronomy, it is rarely that you actually get to lay your hands on the thing which you're studying. Figuratively speaking, it's your satellite which is making these measurements, but you can't really measure anything directly. Okay, now you can go to the moon and also Mars. So that's the extent of the story. And it was really dramatic because a lot of things were happening very quickly. I predict something this year, and next year somebody measures it and tells me, yeah, that's right. Yeah. So that's fantastic. Okay. Now, so the sort of solution which he came up with was of this nature. So this is the sort of equatorial, or let's call it the ecliptic plane, the plane of the Earth's path around the Sun. The Sun is at the center. This is the Earth's orbit. Earth is denoted by this sign in a lot of astronomical literature. And now these red lines are showing the magnetic field which would have originated from a given point on the Sun. Right? Let's maybe draw something to talk about that. So what is happening really is that if I am at any point on the Sun, the solar wind which is flowing out of here is moving radially, right? But the Sun is rotating. So while this particle has moved out radially, after a while the Sun has rotated here. So let me call this A. So after a while A has moved here. Now this guy which has been thrown out is going to continue to move with its speed. It is no longer connected to the Sun in some way, so it is only going to move radially out. So in the time the Sun has moved from here to here, this particle, let's say, has moved from here to here. Right? Now the next particle which is being emitted from here. And I can keep following this progression. Now the Sun has moved here, this guy has moved here, this guy has moved here, this guy is sitting here. And I can begin to draw a path like this. Now I said that these plasma and magnetic field are like beads on a wire. So the magnetic field which is tied to this place is still the same. Right? So even though at all points on this spiral, the plasma is moving radially out, the magnetic field is following this Archimedean line. Right? And this is giving me the locus of all the points where the solar wind is originating from, that particular place on the surface of the Sun. Right? So now if you were to assume that the surface of the Sun was sort of homogeneous, that it has the same sort of magnetic field everywhere and therefore the same sort of solar wind speed with which things are going to emerge, you are going to end up with something like these spirals. So if you were to drawn the spiral for a 400 kilometers per second sort of a velocity, which is what it really is in the Earth's equatorial plane, this thing will cut the Earth's orbit at an angle of about 45 degrees. If you were to increase the speed quite dramatically, now because between these successive timestamps you move much further out, the spiral does not have the time to develop that structure, it is much more drawn out. Right? That is what those yellow curves show you. So, in reality, the things are a little more complicated than that. Right? And this is what became known as the ballerina skirt model of solar wind. What it is trying to show is that, well, we said that the sun has magnetic field. One hemisphere is dominantly north, the other is dominantly south. So there must lie some region, some boundary on the sun, which is going to separate dominantly north from the dominantly south. And let's assume this thing was that line. And what it is trying to show, because this thing is wavy, it is trying to show what would be the gradient, what would be the solar wind which is originating from that. What might that look like as it is going up? So the undulations of this line are what are being reflected as the folds in that. And it is showing you many planets. So if this structure is stable for a long time, right, after 27 days, one solar rotation, you will come back to the same place. And therefore, if I was just looking at it from this way, this thing and this thing, really, sorry, no, not this thing. No, sorry, I can't use this plot to make that plot, sorry. But basically, these undulations here are coming from the undulations in this line here, which is called the current sheet. Okay. Now, the solar wind is really fascinating. I mean, this is very interesting to study for us because all the impact of the sun which is conveyed to us is conveyed by the solar wind. Right? We are sort of immersed in this path of solar wind, and that is what is conveying solar influence to us. Apart from radiation, radiation forces will come. So the heliosphere is defined to be this region around the sun which is dominated by the plasma of solar wind. Okay, wherever you find plasma primarily of solar origin, that is the region of influence of the sun, that is what is called the heliosphere. One of the first actually not one of the first satellite. See, most of the satellites which we have, their orbits lie in the ecliptic plane. Right? They just circle around the sun, but in the same plane as the Earth takes to go around the sun. This guy Ulysses was one of the first satellites which did a polar pass of the sun. Okay? So it sort of went perpendicular to the ecliptic plane to do a first measurement of what the solar wind is like as you go away from the ecliptic. So these are the data from that particular satellite. So on the x-axis and y-axis, both of them are actually showing you velocities or speeds. This is the x component, that is the y component. So the length of the vector tells you the speed of that. The red and the blue, they correspond to the direction of the magnetic field. So red is going out, blue is coming in. Okay? And what it is showing you is that in this region, you have, say, something like 350, 400 kilometers per second of solar wind. As you come out here, you have something like 800 kilometers per second of solar wind. Once you are outside this region, which is maybe about 30-35 degrees of geographic latitude, all the way through, it is more or less the same. There are some fluctuations, but there are no dramatic fluctuations. As soon as you come within this region, the equatorial belt, where you also have the sunspots and other activity also happens there, that is where the velocity suddenly drops. Not only it drops, it can have very large and systematic variations. This is not random. There are well-defined structures which are going up and down. That is because there is something happening there which is giving rise to that structure. It was really dramatic when they published this for the first time. So where do the limits of the heliosphere lie? Well, as a physics student, you would say that, okay, I have to basically get pressure balance. Right? whenever the pressure from my heliospheric plasma becomes equal to the pressure because of the interstellar medium, that's where it should happen. So that is indeed how it is defined. And just for terminology, humans are biased towards themselves. So everything inside the Earth's orbit we call inner heliosphere. Everything outside that we call outer heliosphere. Now it really did make big news when the first man-made object. So this was a quest to find out where do you actually achieve this pressure equilibrium. Right? So there was these satellites, Voyager 1 and Voyager 2, which were launched to exactly answer this question. It was, I forget the numbers, but I think it was something like a 27-year wait after the launch of the satellite till the time it went to the edge of the heliosphere. So some projects are much longer than a thesis project. And there were two of them, Voyager 1 and Voyager 2, and in fact it so happened that when Voyager 1 was crossing this boundary, it malfunctioned. So now you've waited 27 years for your guy to reach there, and then for those few hours when you really needed that data, it is not working. That was sad, but it happened, and after that it was recovered again. These are from Voyager 2, and it turned out, it just shows you the place where they believe they crossed the heliospheric boundary, and that is at some 90-something degree. Okay, so it's well outside. Pluto is no longer a planet, but it's still well outside the orbit of Pluto. Not only that, Voyager 2 gave them sort of bonus in the sense that it turned out that Voyager 2 crossed this heliospheric boundary multiple times. How could that happen? Now this guy is going out. So what that basically said that this boundary is dynamic, which is perfectly fine because your solar wind is dynamic. Interstellar medium, whatever is happening there, is also dynamic. Though I think the dynamics of the solar wind is much more dominant in this case. So because of the change in pressure of whatever was coming from the solar wind towards that direction, the place where you find this equilibrium is going to shift back and forth. And so it so happened that the Voyager 2 crossed this boundary thrice. So bringing some solace to the people who missed the data from Voyager 1. This is a movie which is not playing, and I don't know why. Oops. Sorry, excuse me a minute. I'm not sure why this is not playing, but if you were to look for a CME simulation or a CME movie in NASA, one of the links you would come up with is this. What it shows is basically this is the ball of the sun. At some point, there is a huge eruption on the sun, and it shows a cloud of plasma which is moving towards the Earth. As it moves towards the Earth, it begins to interact with the Earth's magnetosphere. What is the Earth's magnetosphere? It is, Earth itself is like a bar magnet, right? We have a north magnetic pole and a south magnetic pole, and therefore lines of field going all around. The CME also has some magnetic field, and now there are these two magnetic fields which are going to interact with each other. And this one shows a case in which the CME can actually have a strong influence on the magnetosphere, and that really energetic plasma can come to the Earth's magnetosphere and give rise to aurora. Well, aurora is there all the time, more or less. Some days it is brighter, some days it is not so bright. And these are really the energetic electrons from the solar wind which are coming to the Earth's magnetosphere and have been trapped such that they are now being guided by the Earth's magnetic field rather than the magnetic field of the solar wind along which they were originally flowing. Okay. The whole point of showing you this, and which was also the thing which I wanted to make the last point in my presentation, was to say that these things can have a significant impact on us now. So now we rely a lot on technology. A lot of this technology is really tied closely to what is up orbiting at from geostationary heights at 36,000 kilometers to heights of a few hundred kilometers for our GPS satellites. We have International Space Station at again about 100 kilometers, 100 something kilometers, where we have human beings, where we have a constant presence of human beings. Right? It's never uninhabited. We always have a few people there. Now, what happens is because of these solar wind, these huge eruptions on the sun, which are given the name of coronal mass ejections, they are really massive in terms of the mass which they carry, and they're really hot plasma. They can give rise to, if they were to get into the Earth's heliosphere, they can give rise to all sorts of things, ranging from just increasing the density of the atmosphere, which would mean that any satellite which is up there is now going to experience larger drag, which means that its orbit is going to decay, it's going to come down a little bit, which means that, well, if you want that guy to survive, you have to boost it up, which means you have to spend fuel. So it's going to reduce the lifetime of your satellites which you've launched. Any solar cell which is directly impacted by these very energetic radiation, it loses its efficiency by a couple of % every time it goes through such an episode of experiencing a coronal mass ejection. So it's also reducing your lifetime of the satellite because it's reducing your ability to generate power to sustain the satellite. It can introduce enormous amounts of currents in the ionosphere. And today on the Earth we have our power distribution grids, which are like very long conductors which are there on the surface. Right? So you know that a current, if I have set up a huge current somewhere, it is going to also induce, it's going to give rise to a magnetic field which is going to reduce current in some other conductors. And if we have these very, very long conductors in the form of our electricity grid, they become very vulnerable to something like this. And that can actually give rise to catastrophic failures of power grids. So, and living in India, we don't have to really worry about it because this sort of stuff happens close to the poles. These currents are set up close to the poles. So it's really the Russians and the Canadians who have to worry about it. Okay, but Quebec has lost power at least twice because of something like this. And when it happens, it blows up transformers, big expensive things which you don't usually have in stock to replace. So it's very disruptive when it happens. It also gives rise to GPS navigation problems. Problems to the extent that you would not be able to see your GPS satellite at all. Your cell phone won't be able to detect, won't lock on to the signal from the GPS. You certainly can't land a plane when such a thing is happening on the basis of GPS. In fact, that is why every plane must have an independent navigation system. They don't rely on GPS at all. Okay. So to give you some examples of what these things might look like, these are also movies. Well, okay, I'll tell you where these movies come from, and you should go and take a look at some of these if you have not already seen them. They are from a satellite by the name SOHO, Solar and Heliosphere Observatory. And there's a website which is called SOHO Theater or something like that. I have it bookmarked so I don't have to remember the name very often. I'll make sure that the name reaches you, but if you were to look at SOHO, LASCO movies. The particular instrument is called LASCO, LASCO. The satellite is called SOHO. I think just SOHO, LASCO, and the keyword movie will take you to a place where you will see very spectacular ones. These ones are among the spectacular CMEs. They took place on the Halloween day, 28th of October was the Halloween, so they are called the Halloween CMEs. They were so bright that you could see the aurora because of them down to latitudes of something like 40 degrees, which I actually happened to see because at that time I was living close to Boston, which is at plus 42 degrees latitude. It was very cold, but it was worth it. What you're seeing here is really an artificial eclipse has been created. This is something called the operating disk. This is a satellite which is sitting at L1 point, the Lagrange 1 point, which is between the Earth and the Sun, about 1 million kilometers from the Earth. That's a place where gravitational pull of the sun and that of the Earth is roughly equal. So you sit there and you get an uninterrupted view of the sun. Among the first satellites to go there. And so it creates an artificial eclipse so that you can see the Thomson scattered light from the electrons which are all around the sun. What you're able to see really is that there are these very bright things which are traveling out, which are very bright fronts which you can see. This particular CME happened to be directed towards the Earth. So now imagine something going out like this. Right? So that thing is going to appear like a halo around the sun. Right? So the ones which are either coming directly towards the Earth or going directly away from the Earth, both of them appear like halos to us. This is called the C2 coronagraph. Its field of view starts at 2 solar radii. This white circle is supposed to mark the disk of the sun. This is the same idea, except that this field of view is much larger. It starts at something like about 6 solar radii and goes up to something like 13 or 14 solar radii. So you can see basically, you can see it pass through the field of view of one imager first and then through the other. And that is what people have been using to figure out the direction of propagation, the speed with which it has been moving, and so on and so forth. Here is a different example, which fortunately is not a movie. So you can see the progress of something as a function of time. Now, this I think is the last thing I want you to leave with. So this is now a cartoon which is talking about where here's the sun, here is this what the CME looks like, this is the Earth with its sort of magnetic blanket. That magnetic blanket is really very important. That a lot of people believe is the reason why life exists on Earth and other non-magnetized planets don't have this. Because this is needed to sort of shield us from these very energetic particles from the sun. Okay. So let's say there was a CME which has a magnetic field orientation like what I've drawn roughly, and it is coming and hitting the Earth. And it takes about 2 to 4 days depending on how fast it is traveling. If the magnetic field here is also parallel to this guy, because we know like magnetic fields are going to repel, right? So this plasma is going to compress this because it is moving very fast and it is really energetic, but won't be able to penetrate this blanket. That plasma will basically flow along the sides. And it will not be geo-effective, is the term which is used. On the other hand, if it was something like this, what will happen is that once it comes here, that business of magnetic reconnection which I was talking about earlier will happen. That will allow this plasma to follow now the lines of magnetic field of the heliosphere, which will bring it to the poles. Right? That is why I was saying that if you are in polar regions, you have more issues than if you are here, where we are. But some of the issues are global. Whatever the ionospheric currents it is going to set up, they will have a global impact. This is a movie of some aurora which was actually observed in response to one of the CMEs. That thing is also supposed to be a movie. I don't know why this is the lucky one and that is not so much. This is probably a good place to stop for me because I've overshot my time already and I'll be eating into your lunch. So if you have any questions, I'm happy to try to answer them. You guys are here for how long? 2 weeks? 1 week? 1.5 weeks. So I work at NCRA, room number 222. If you have any questions, you can first drop me a mail and maybe we can make an appointment. So div@ncra.tifr.res.in. Feel free to get in touch if you have any questions. And if you have questions right now, I'm happy to take them.
Sir, why do we get such hot gas around the sun, such hot plasma? Because it is expected that the temperature should keep dropping, and when we go to the outskirts of the sun, we should have less energetic particles. So why is that such high temperature?
So it's true that we did not expect it. However, about some things we don't have a choice. It is there, right? So it is now our business to try to understand and explain why is it there. And that I did give you sort of a preamble to the story that we believe the energy is coming from the magnetic fields. There are 2 well-established ways of extracting that energy. neither of them, whatever evidence we have so far, meet all the needs for giving rise to coronal radiation. So it's unexplained and it was not expected.
You said that paths in the sun rotate at different angular velocities. So how much of this would contribute to the Coriolis effect, and does the Coriolis effect contribute in terms of solar winds?
So what rotates at differential velocity is really what is beneath the photosphere. In many ways, that is not directly connected to the solar wind. What that does lead to is giving rise to this cycle. That Coriolis effect is what is the reason for this convective cycle, which you see.
How is CME, solar flares, and solar wind different?
See, solar wind is there all the time. CMEs are specific events which are specific release of large amounts of energy. So there was some big active region which had a lot of energy stored in some magnetic field. It exceeded some critical threshold and there was an explosion, which was basically relaxation of this magnetic field. That energy got deposited in this plasma, which is now shooting out at a very high speed. So CME is a specific event. It is usually associated with a flare. Solar wind is there all the time.
During the minimum of the sun solar cycle, the solar winds are maximum at the upper latitude.
Are fastest at the higher
Fastest.
latitude.
And we observe sunspots maximum over there.
Sorry, say that again. During minimum, you said solar winds are highest away from the equatorial region.
And you observe the sunspots to be maximum in the upper latitude?
No. So during solar minimum, there are hardly any sunspots. Right? And the sunspots usually don't go beyond plus minus 30 or 35 degrees. They are always in an equatorial belt within plus minus 30 degrees.
Why is there a variation in the solar wind?
So, simplest way to think about that is that if there is a variation on the surface of the sun, you should expect to see variation in the solar wind. Right? It is just whatever is arising from that. Any other questions?
So, can you explain the dynamic curve of the solar system?
Can I explain more?
You had talking about the folds in the parallel diagram.
Ballerina, yeah. So, okay, that is just a visualization to give you a sense for the solar wind which is arising from the contour on the sun, which is separating the north from the south. What would that look like in 3 dimensions? That is what that diagram is trying to do. So it is tracing out just this line radially out, while the sun is rotating in the background, and it is then drawing these various loci from each point, trying to connect it to where it came from on the surface of the sun. That is what it is trying to do.
Sir, when you talk about the heliospheric boundary,
So heliospheric boundary is the place where the plasma of solar vision, that is a solar wind, meets or comes in pressure equilibrium with the interstellar medium. So because this plasma is magnetized and the other plasma also carries some weak magnetic field, these plasmas don't mix. It becomes like a bubble in which has a boundary. So all the solar plasma is inside, interstellar plasma is outside, and this forms the boundary.
in the equatorial boundary region, they cancel each other so that solar velocity is minimum.
No, sorry, what cancels each other?
I mean, there was the radiation, there was the minimum near the equatorial plane. I mean, that's the shown on the plot.
Okay, so we are now talking about something else. You are not now talking about the speed of the solar wind. Right? The speed of the solar wind does show a minima around the equatorial belt. That is because that is the part of the sun which has the smallest number of open magnetic field lines.
How about using the radio data of
So I did not talk about that at all because it takes a while to build up. Why would you want to do radio? What is it that is interesting about radio? That is of a lot of interest to me because that is what I do. But I thought that for you, the more general introduction to the sun and the heliosphere would make more sense rather than take you to one particular part of the electromagnetic spectrum and its techniques, etc. So it's a long answer. It's maybe not enough time for it right now.
In the diagram with the magnetic field of the Earth, there was something magical pause that from the poles the magnetic field lines are not coming out radially, instead they're going away from the sun. What is is it because of the sun's magnetic field?
This guy, right?
Yeah.
So magnetic field lines will never come out radially. Right? This is like a bar magnet, except at the poles. So
No, I'm asking why is it going away from the sun? Like,
this guy, yeah. It is the same situation exactly as you have at the heliopause. Right? Now, Earth has its own atmosphere, it has its own ionosphere, so its own plasma which is being confined by its own magnetic field. And Earth is in an orbit around the sun. There is also the solar wind flowing out. So there has to again be a pressure balance between the region, between the plasma which is tied to the Earth and this wind which is flowing across. And that is what is giving rise to this shape. Okay, very good. Thank you very much. Like I said, if you have any questions, get in touch and maybe we'll be able to find a time to meet. Thanks a lot.